substitution and find the results. And here, for this problem, although alpha is equal to 2, okay, but once you try to solve your system, you ended up having the dimension here is 1 vector, although the algebraic multiplicity is 2. Am I right? So once more, it's not like the previous problem that when we found that the algebraic multiplicity is equal to the geometric multiplicity. Here, no, it didn't happen. Note that the eigenvector is -1, 1, and -0, non-double-zero, all linearly independent vectors, and we cannot get a basis for R3. We cannot get the diagonalization for this matrix consisting of eigenvectors of C. Note that the characteristic polynomial may have complex roots, but we don't solve complex roots. We are keeping our discussion in this part or in this course with the real numbers, okay? In other courses, like in engineering or something, you will find in FCT we are getting a complex eigenvalues, okay? Eigenvectors. So the algebraic multiplicity, once more, it is the number of repetition of the roots of the characteristic polynomial. This is stated in here. We already know it from the beginning of our lecture, if you remember. Note that by the fundamental theory of algebra, a degree of n polynomial has n roots. Maybe real or complex. He's talking about a minus lambda I. So once you solve this equation, you may have roots, positive, negative, or complex. Okay. So once more, he's stating that for lambda is equal to minus lambda 1, that means the eigenvalues are alpha 1 up to alpha n. Alpha n, as I told you. Once more, let lambda be an eigenvalue of n by n matrix, the set of eigenvectors associated to the eigenvalue of lambda completed with the 0 vector, which is AU equal to lambda u. That's the homogeneous system that we depend on in order to evaluate all of our eigenvectors, okay? And those eigenspace, or those eigenvectors will form the eigen subvector space, okay, that we are dealing with. The algebraic multiplicity once more, and here he is giving you the geometric multiplicity, which is the dimension of the eigenspace, exactly as we did. Once you finish, you will count your vectors, which are the basis of the eigenspace, and it is the geometric multiplicity. Okay, once more, that's the introduction. Therein, let A be an n by n square matrix, and those are the eigenvalues. Counting multiplicity and complex numbers, then we will have, those are two important propositions. And probably these propositions are important. You may have problems targeting these two special points. The first of them is, remark, the multiplication of the eigenvalues, will equal to the value of the determinant of the matrix. So if I have a matrix, square matrix, and we're getting the eigenvalues, if you get the eigenvalues and multiply them together, it is equal to the value of the determinant. Are you with me? That's remark number 1. Remark number 2, do you remember what's the trace? The sum of the elements on the principal diagonal. This is what's called the trace of a matrix. So the trace of the matrix is also equal to lambda 1 plus lambda 2 plus lambda 3, if you add them together. Okay? So it's two very important remarks. If you multiply your eigenvalues, it will equal to the value of your determinant. And also, if you add the elements on the principal diagonal altogether, it is the trace of a matrix. So, and you know what the trace from the beginning of our course, okay? With the types of matrices and stuff like that, okay? So it's very, very important two remarks. Also remark that for A be an n by n square matrix, lambda 1 up to will be distinct eigenvalues, okay, of A, and U1, UK are the respectively corresponding eigenvectors. They will be, since lambda 1 up to lambda k are distinct, so they are different than each other, the new eigenvectors will be linearly independent, which is connection into vector spaces, okay? This is also a very nice remark. Yesterday, when we started our eigenvalue and eigenvector session, we started by finding the eigenvalues, getting the eigenvectors. From the eigenvectors, if the matrix is symmetric, you will get the model matrix. Okay? The model matrix, when you have your first vector, second vector, as columns in this matrix, then I will normalize it. If you remember how to normalize a vector, you will divide the components on the sum of squares of its components. You will see it here. Okay? And in this manner, we will have, if the matrix is symmetric, we will have orthogonal, if you remember, eigenvectors. And if they are orthogonal, they will lead to orthogonal matrix. And one of the beautiful properties of orthogonal matrices is the transpose is its inverse. Okay, all of this in the sake of getting similar matrices. So instead of dealing with an A matrix, I can deal with a diagonal matrix where the elements on the principal diagonal are the eigenvalues. Okay? This could happen. So let A and B be n by n matrices. It's introducing this part. Okay? We say that A and B are similar matrices if there exists an invertible matrix S such that B is equal to S minus 1 times A times S. Okay? So once more, if A and B are n by n similar matrices, okay, then you will have the invertible matrix that I told you about. And remark also the characteristic equations of the A matrix and the similar matrix, they are equal to each other. So solving them will get the eigenvalues exactly the same. Okay, in linear transforms, we already saw if I'm moving from R3 into R3, I can get the matrix of that transform, I can get the eigenvalues and eigenvectors corresponding to them. Okay, so E and ED linear mapping, a non-zero vector U is called the eigenvector of the transform exactly the same. This is the diagonalization, D is a diagonalization from A. It will happen if you get S minus 1. All of this is covered. One of the huge advantages, if you remember yesterday, we started with the first slide. The first slide, I don't remember if you attended or if you were in the classroom or not. But the first slide talk about if I have a complete matrix and if I have a diagonal matrix. There is a huge difference between dealing with both of them. Because the diagonal matrices, if you multiply it in itself, all you have to do is to square the elements on the principal diagonal. Okay? That's an advantage. It is explained here. A to the power of n, if you are dealing with a complete matrix from the beginning, you will have to multiply it in itself. 2 times, 3 times, 4 times. But if A is similar to this matrix, or you have the diagonalization of the matrix A, I can replace A by this guy. And I can replace the second A by this one. And replace the third by this one, and so on. Remark. بص للسلمة S minus 1 times S will vanish, it will be R. And the D times D is going to be D squared. This is multiplying A times A. If repeated A3, it's going to be D cubed. If repeated n times, it's going to be D to the power of n. So instead of multiplying the matrix in itself n times, I can multiply the diagonal form in itself n times. Do you read me? And that's the similarity which makes everything much smoother and easier. And then by n square matrix is diagonizable if, so it is diagonizable if and only if A has linearly independent eigenvectors. And the linearly independent eigenvectors will be got from a different eigenvectors, eigenvalues, okay, of a symmetric matrix. That's there exists a basis of R n consisting of these eigenvalues. A linearly independent set will form a basis for the whole space that you are dealing with. So if I have a matrix 3 by 3 and you have linearly independent eigenvectors, those eigenvectors will form a basis for R3. If you have a 2 by 2 matrix, it's a part of R2, صح? So if the eigenvectors are linearly independent, so the basis, which are these eigenvectors, will represent the basis for R2. That's this remark. Okay, once more, this is, as you can see, it's a beautiful matrix. It's a symmetric one, صح? So solving this system or this matrix will develop all what we talked about. So if you try to evaluate, you will have lambdas equal to 0 and lambdas equal to -2. Look to the eigenvectors, princess, you will find these eigenvectors are perpendicular in each other. Because 1 times 1 is equal to 1, 1 times -1, the sum is equal to 0. The matrix that will be developed from these two eigenvectors, which is called the S matrix, I can get it right now, which is the first eigenvector will be the first column, the second eigenvector will be the second column. Are you with me? Look to this matrix, I will need to normalize it, or to get it to a unit matrix, okay? This is very simple. I will divide this guy on the sum of the squares, okay, of its components, which is 1 to the power of 2 plus 1 to the power of 2, which is gonna be √2. So actual S is gonna be 1 over √2, 1 over √2. In a similar manner for this guy, you will have √2. So it's gonna be a 1 over √2 minus 1 over √2, and this is the S matrix. And it is an orthogonal matrix, since its two columns are perpendicular to each other. So S minus 1 will equal to S transpose, which means that the transpose of this matrix is its inverse, which is, once you try to transpose it, it will give you the same matrix. Okay, are you with me? Now I can get a diagonalization, which is multiplying S minus 1 times A times S. You will get a diagonal matrix with the elements on the principal diagonal, your eigenvalues, which are 0, then -2, the remaining elements are zeros. And this is exactly what we got in here. That's the diagonal matrix, and that's the S matrix required for this process. And if you multiply the S matrix and S minus 1, you will find, that's 1 small, that's the inverse, that's your matrix, and that's the A matrix, okay? Of course, you find a half, -half, because he didn't normalize this matrix, divided on √2 and √2, okay? So if you try to get its inverse, it will be in this shape. But here, the inverse is just only the transpose, and you will have its exact same result, 0, 0, and for the matrix, 0, 0, 0, and -2, okay? Note that there is not a unique way, for instance, considering beta -1, 1, -1, 2, and 2, consisting of eigenvectors associated respectively to the eigenvalues, lambda 1, -2, and -1. So this could be the inverse of this matrix if you are using other numbers. That's also another advantage of normalizing your matrix. You will have just only one form, okay? Because you are skipping the point. مش واضح انك فاهمين. بصي الايجن اللي انا استخدمتهم هنا، انا استخدمت 1 و -1 1 صح؟ ما هو ال 1 ده كان ممكن يبقى 2 2، ده ممكن يبقى 3 و 3، ده كان ممكن يبقى 4 و -4. في حاجه تمنع ده؟ مش انت لما تيجي تحسب الايجن فاليو في الايجن فيكتور في الاخر بتيجي على يو 1 1 و 2، انا هحطها بواحد، احطها باثنين، احطها بثلاثه، احطها باربعه، تنفع ايه؟ فده هيغير دول، هينفع ايه ارقام، فيغير لي دول. فهو هنا بيقول لك انه مفيش نوت ذات there is not a unique ايه؟ لانك ممكن تختاري ارقام. اوكي؟ for instance considering 1 -1 بدل 1 1 انا حاططها 2 مين؟ عشان هنا كده بقى حصل ايه الاختلاف. لكن عشان لو انا استخدمت الاورثو نورماليزد موديل ماتريكس، يعني making this vector as a unit vector and that vector as a unit vector, I will get the same solution. Okay? It will be stated down the road. That's a 3x3 matrix, a symmetric matrix, beautiful matrix. If you try to solve it, it's going to be easy. You can find that lambdas equal to 0 and distributed 2 times, and the other lambdas equal to 3. That's a type. It's 3, not 6. Okay? This is once, that's twice. That's the algebraic multiplicity of 2. Okay? If you try to solve them, you will have your values, as I told you, you will get your S minus 1 exactly in a similar manner. And so I will be able to get, this is the diagonalized form. That's the 0, 0, and 6. Okay? Okay. The quadratic forms are the final thing in our course. The quadratic forms are really very simple. What's the time now? Let me check. It's at 10:20. I can do the quadratic forms next lecture, but I will give you a hint. Since it's really very simple to know about them. And we already know partially about them, okay? So, the quadratic forms mainly connects the variables x, y with the eigenvalues of the eigenvectors. So, in a very simple way, if I have, for example, if I have x squared plus a 4 of x and y plus 2y squared, this is a quadratic form because it contains the elements with the power of 2. I can find the matrix representing these guys by considering how many x's do I have or how many components. It's the x and y, I mean R2, صح? So I will put them x, y as a row, then I will have my square matrix, then I will have x and y as a column form. Okay, how to get the matrix with the numbers, okay, or the matrix that I will use down the road in order to find the eigenvalues and the eigenvectors. All I have to do is to look to the coefficients of x squared, which is 1 and 1. So the coefficient is positive 1, and the coefficient is positive 1, and its position is 1 and 1. Okay, now I will get to this element, which is y, which is number 2. Y squared, it means 2 and 2. So the element in the position 2 and 2 is equal to 2. Okay, what about this number? It is the first x and second x, so it's a 1, 2. I will divide this number with its sign, putting half of it in the element 1 and 2 and the other half in 2 and 1. This is how to get the matrix. So divided by 2 because this is the 1 and 2 or 2 and 1 added together. Okay, so I will divide in 2, put half of it on the element 1 and 2 and the other half on the 2 and 1. Another problem, let's say for an x squared minus 3y and x plus a 6 of y squared, it's gonna be, or let's do minus 6y squared, it's gonna be exactly the same. For the quadratic form, it's gonna be an x and y, this is 1, that's 2, and that's the matrix that we are dealing with. Here we go, that's an x, that's an y, and very simple, the coefficient of 1 and 1 is equal to positive 1. The coefficient of 2 and 2 is negative 6. Then I will divide on 2 with the same sign. So it's going to be minus 1.5 and minus 1.5. Are you with me? Like, what if I'm dealing with a quadratic form in 3-die? It's exactly the same. So, for example, if I have x cubed, x squared plus 2 of an xy plus 4 of an xz minus 6 y and z plus y squared minus 4z squared. I can write the quadratic form. This is a quadratic form but in 3D. Okay, so all I have to do is to write, I'm on R3, am I right? So those are x1, this is x, y, and z. I can use x1, x2, x3, it's exactly the same. Okay, and that's your matrix in here, and the 3 coordinates, which is x, y, and z. I would prefer writing 1, 2, and 3. Then the element 1 and 1, which is going to be x squared, which is positive 1. The element y squared is going to be 2, 2. So y squared is going to be a 1. And z squared is going to be 3, 3, which is negative over 4. Then I will go to x and y, which is the element 1 and 2. I will divide it into half of it in 1 and 2, and the other half in 2 and 1. Okay, now I will go for xz, which is 1 and 3. I will divide this number, half of it in 1, 3, and the half of it on 3 on 1. Then I will go for 1 and 3, which is xz. So negative 3 in 2 and that, and in negative 3, in 3 and 2. This is how to get your matrix. It's very, very simple. Also, I can get the quadratic form from the matrix. So if I give you, for example, the matrix, which is 1, 0, 2, for example, 0, 2, 3, negative 1, and 4, and I need the quadratic form.
X squared.
So it's gonna be, yes, it's gonna be x squared, huh? Plus 3, y squared, plus 4, z squared. Then 0 in xy. Then 2 times 2 in xz. So it's going to be a 4 xz. Then I will have negative 1. This is yz. This is yz. Second, third, yz. Okay, so it's going to be a negative 2yz. Okay? Just a second. This is, yes, it's correct. I don't have xy because the xy's are equal to 0. Now, I can get the quadratic from a matrix or a matrix from a quadratic form. Okay. So once more, this is a11 x1 squared, a12 x12. This is the positive 2 that we used, and so on. So I can simply write the quadratic form as a row matrix times my a row matrix containing the axes or the components, and a column matrix containing also the axes times the matrix that contains the coefficients. Multiplying all of them together, I will get my quadratic form exactly as we did. Okay. This is a symmetric matrix, exactly like the ones in the beginning of our slides, and he's introducing all the steps. I will leave this part for next time. It's more than enough what we did today. Then we'll continue next lecture, inshallah. Thank you very much. I believe I've shared also 2 videos from the last year containing the remaining of this part just to be with you. And I will also upload this lecture, after which, with the beginning of next week, I will upload plenty of revision lectures. You still have work next week, am I right? Lectures, okay? So we will be fine. Thank you.